This video is going to go through how we actually quantitatively work with vectors in terms of mathematical operations such as adding and subtracting. When I say quantitatively here, I mean that in contrast to the graphical methods that we've done so far. A big part of this is going to be using correct vector notation, practicing that in terms of using the right notation for vectors, their component vectors, and the components themselves, i.e. the magnitudes of the component vectors. I think all of those things are much more clear in the written notation than in using the spoken terminology for it. And part of that will be breaking vectors into components. So these are things that you should already have seen, but now we're going to practice. And the big learning outcome that this connects with is, again, problem solving, that many cases in physics you're going to be, for instance, trying to find maybe a net force, and a big part of that is going to be working with vectors. So you're going to see things like this over and over and over again, and you're just going to need to use it as one of your mathematical tools. So the first thing that I would like to do is really motivate why we need to work with components. And part of why I say this is because I've seen students make the mistake of taking two vectors, so we want to add vector A and vector B to create vector C, and perhaps you've been told the magnitude of vector A and the magnitude of vector B and the angles they make with the axis. What I see students do frequently is to actually just add the two angles and add the two magnitudes, and that is definitely wrong. So I haven't actually given you the two angles for these initially in the problem, so let's just say that this one's 45, which I know it is, and let's say this one is 30, which it isn't, but I think it's close to 30. So if I just use the graphical technique that we've talked about before, and I wanted to add A plus B, I would draw my vector B, and I can actually then just move it to the tip of A, and vector C then needs to be what connects my origin here with the tip of that vector. And I haven't done a great job drawing it, but that's roughly C. So, and the reason for that was because this vector here was in fact B. So let me make that blue. So that's how we do it graphically. And it looks like maybe it's something like, I don't know, 7 on the x-axis and 5 on the y-axis. Oh, sorry, my axes are missing directions. I'm sorry about that. And if we were to just look at the angle, though, the angle that the C vector makes with the x-axis is actually in between the A vector and the B vector. If we were to just add these, we would get 75 degrees, which is almost straight up. And that's definitely not what you get when you add these. So again, you must use components, and a frequent mistake that I see students make is just adding the angles and adding the magnitude. So please, please, please don't do that. It's not the right way to do this. So let me clean this up really quick and show a little more carefully than I can draw by hand B broken into its two component vectors and A broken into its two component vectors. And one thing that's really helpful whenever you're doing this is to really clearly denote that we don't have a total of 6 different vectors per se that we're adding right now. And so in this case, I've broken B into dash lines that correspond to it, and so forth. So in this case, we've broken the A vector into 2 component vectors. Each of these is a vector because it's not just a length, it's a length with a direction. Okay? So now, I've broken them into vectors, and what you can now see is if all I need to do is take my original equation and plug my A vectors in for A and my B vectors in for B, that now my C vector is actually the sum of these 4 vectors. Now that might not seem like it's made it any simpler, but remember that, I can move my vectors around, and if I move my B vector from just being the component starting at 0 to my tip of my A vector, my X component vectors, you see that now my Y component vectors kind of add as if they are one-dimensional vectors, and my x components add as if they are one-dimensional vectors. So what you're basically doing, you're combining these two, and then you're combining these two. But these are as if they are each 1D. And adding 1D vectors is very, very easy to do, because all you literally have to do in that case is actually just add the numbers. So the other thing to keep in mind, though, that also makes this a little bit easier, is that our C vector is equal to its components as well. And remember, this is again just by definition how it works when you're breaking things into components. So finally, I can think about the fact that this could actually also plug into this equation. So now that I've added my x vectors and I get something in this direction, and I've added my y vectors and I get something in that direction, before I combine it all together, I can think about the fact that my x and y components of C are each going to lie in these directions. So by adding my x components of A and B, I get one big vector in x, which is C. I add my y components of A and B, I get one big vector in y. That's my y component vector of C. So I haven't yet combined the final thing together, but by using this idea that my C vector can be broken into components, you now hopefully see what's happening. Now, something I want to point out here that's very important is that everything in this equation says x, right? That's only x. Everything in this equation is y. So something that's really important, a mistake that I see students make very frequently, is that they start mixing x and y together, or parallel and perpendicular if that's your coordinate system. Please don't do that. Please keep in mind that anytime you're working with components, your equation should only have x in it. Here, your equation only has y in it. And that's even going to be true for kinematics. Like whenever you're working in two-dimensional motion that we're going to get to next, your kinematics equation should only have x components in it, or only y components. You should have one set of equations for x, one set of equations for y. So the same thing happens here. So finally, we've had our C vectors, and note that we can form our total C vector by basically taking, for instance, our y vector and just moving it tip to tail to our x vector, and there you go. And note that that's pretty much what I drew earlier when I had made my b vector and moved it to be tip to tail. So we get the same thing, either doing this graphically or by doing this numerically. Part of why this is going to matter and why you are frequently going to need to do it quantitatively is that you might have decimal values, and obviously if you know that your answer is a whole value, you might be able to carefully graph it. But once you're working with a bunch of decimal values, it really can only work quantitatively. So please be careful about that. But again, you get the same answer if you did it graphically, but here we've been able to do it quantitatively. So I want to show you what this is going to look like in practice. Again, that first part I'm just trying to motivate why we are actually using components. Now I want to go through and show you what that's going to look like in practice. And so same figure we had as before, showing all of those components. And again, our equation here is what we've already found. Now what this is going to look like, and again, it's important to remember your notation. Note that every quantity I've shown so far has that little vector symbol over it, meaning it's a vector. But we can think instead of the vectors about their magnitudes. And since all of my x components are in the same direction, this is a 1D problem, which means I can just think about magnitudes as long as I also consider my pluses and my minuses. So I'll show you what that means in a little bit, but again, make sure that you're keeping track of whether it points to the right or left when you're doing a 1D problem. So what that means, since this was all in the x hat direction and this was all in the y hat direction, is I can break it up into a unit vector and my component vectors. And the reason I can do that is that by definition, just as I was writing things before as vectors, I can always write my vector, for instance my c vector, as the magnitude of its x component in the x direction plus the magnitude of the y component in the y direction. And that's completely identical to writing it as the sum of my x component vector plus my y component vector. It's the same thing. So what you're typically going to do is basically use this equation where you just take the value, your component of your a vector in the x direction, the component of your b vector in the x direction, and so on. Again, being very careful about your pluses and your minuses, which corresponds to vector components. These component vectors pointing to the right would be positive, left would be negative, and so on.